So, Geraint, where are we?
We are in the lovely Surrey Hills.
Mm.
So I'm in Surrey for the month of June as I'm on sabbatical. So I'm working here at the University of Surrey in the lovely town of Guildford,
Mm-hmm.
where I'm catching up on my work on galactic archaeology and galactic dynamics. So it's a relatively new group, a growing group, but their speciality is nearby stars and galaxies, etc. So it's very exciting.
Excellent.
Yeah.
Anyway, I'm here because I'm off to a conference in Rome next week, which will be great. And I've been spending some time with Durham. We've got with the Eagle team there, and we've got some plans for new wonderful simulations.
It's just going to be pretty cool.
Yeah. But our question for today is, and it's almost sunny enough to inspire this question, how does the sun shine?
Yes, how does the sun shine? That's an interesting question, isn't it? Because, of course, people know how essential sunlight is for life on Earth, right? The light from the sun arrives on the Earth, it powers the plants we eat, the plant it powers us, etc.
Mhm.
And as we will talk about at some point, I'm sure, during these videos, you need this sort of gradient of energy, effective temperature,
Yeah.
from hot sun to cold space, and in the middle you have power life.
Mhm.
But the question of these flies are
This is incredible. It's not really showing up. Oh, carry on.
so there's a lot of flies here. So the question, of course, of what powers the sun, right, it's been one that people have wondered about for a long time. And of course, there was this idea that the sun may be like a giant piece of coal, right, burning in space. And it was Lord Kelvin, I believe, who famously did this calculation to show that even if the sun was a ball of coal, it could only burn for a couple of million years, which didn't match with the geological timescales. So the question of what powers the sun was, there must be a more efficient, a deeper power source that people didn't understand.
So another thing that Kelvin did was to say, all right, maybe here's how the sun works. Maybe as things collapse under gravity, gravity pulls them in. There's energy that you can get out of that process, just as when a heavy rock or something falls, you could get energy out of that. That could turn a turbine or something. And so Kelvin did also the calculation: if it's just a collapsing ball of gas, how long can we get a nice shining sun out of that? And again, the number comes back of like a couple of million years, I think.
Yeah,
So
completely.
that doesn't quite work.
Completely out of whack with the geological timescale that, of course, from Darwin and evolution showed that it required billions of years to get basically life to where it is. So, what was the breakthrough? What did people realize?
Well, I guess it probably starts with Einstein's E equals mc squared. Is where what was discovered was that there's this additional source of energy. So, in the very early 1900s, you have a sort of growing feeling that there's something missing from physics. Some weird things are turning up. There's a wonderful book by Poincaré called The Value of Science, Henry Poincaré, in which he says there must be a revolution coming. And one of the things that tells him there's a revolution coming is radioactivity. They've discovered that there's these types of materials that just seem to glow for no apparent reason. You don't have to stick them in sun. You just like radium, for example. You just have a bunch of it, and it just keeps on glowing.
And to give some credit here, of course, we're talking about the work of Becquerel and of the Curies, of course.
Curies, yeah. So they discovered these weird things, and Poincaré says, is this the end of conservation of energy? Is this just the end of the idea that energy is conserved because these things are just making it? But what came out of that eventually, thanks to Einstein and a lot of the other physicists then, I guess we could try and give them all credit, but E equals mc squared is the main one. But actually within mass itself, there is a way of generating an awful lot of energy. If you can turn mass into energy, then you liberate loads and loads of energy per unit mass. Right. And so what was on the basis of that, if there's a way of fusing protons and neutrons together to make heavier elements, that will release energy as mass is lost.
That doesn't quite make sense, right? How can sticking two things together release energy?
So it's easier. Well, the way I think about it is it's the reverse of trying to tear them apart. If there's two things stuck together, it takes a certain amount of energy to pull them apart. So if you think of just gravity, so there's a rock here on Earth. How much energy would it take to take it off the Earth and put it into space? Well, that amount of energy, just ignoring air friction, all those sorts of things, just purely you've got to lift it out of Earth's gravity. Well, that means if you did it the other way around and you dropped it down into Earth's gravity, you would release that amount of energy. So wherever there's a binding energy that holds things together, if you bind things with that energy, it will release a certain amount of energy into the universe.
So let's be clear here. So what you're saying is that if I take helium, right? Nucleus of a helium atom we know is 2 protons and 2 neutrons stuck together. If I take not the nucleus, but the individual parts, a proton, a neutron, and measure their masses individually, and then I measure the mass of the helium nucleus, are you telling me that the helium nucleus weighs less than the sum of the 4 masses?
Yeah, so that's the interesting bit. That's exactly the energy that gets released according to E equals mc squared.
That's freaky, isn't it?
Yeah. So we think of mass as just being the amount of stuff. And of course, if you just rearrange things, they'll be the same amount of stuff. You just put them in a different order. But that's not what we find, actually. It's one way you could think about it, which is sort of hand-wavy way. Any form of energy that something has to carry around with it sort of counts as its mass.
Okay.
So in actually if you have an ordinary atom, most of the mass we think of as being in the protons, the neutrons, the electrons, all that. But actually the fact that the electron is bound up, there's energy there, sort of it contributes a very small amount to its mass. So anything you've got to carry around with you counts. And so anything that gets released in that, it can turn mass into energy and energy into mass.
Yeah.
So once you mess around with this way things are bound, there's a source of energy there to be released.
Okay. So how does the sun do it, right? So we know that the sun... well, let's not just take the sun. Let's take a simple star. A star made just after the Big Bang, right? We know that effectively that is a giant ball of hydrogen and helium.
Yep.
There's 25% helium. The rest is hydrogen. Hydrogen is a single proton with an electron. But in the sun, it is so hot that electron gets ripped off. So it's effectively a plasma.
Yeah.
So you've got this big mass of protons with a few helium nuclei in there. What happens? I mean, the sun starts off as a big ball of gas that collapses, and as the idea of Kelvin, right? As it collapses, it gets hotter and hotter. But something changes, right? Once it gets hot enough and dense enough, what happens?
So the weird thing is that you start off with a ball of protons, and you start making helium, which is 2 protons and 2 neutrons. So where did the neutrons come from?
Oh, that's right, because the neutron has a lifetime of less than 15 minutes.
Yeah.
So if you have lone neutrons, they decay. So there's no lone neutrons bouncing around in the sun, right?
No. So what you said before of you put 2 and 2 together, that's not exactly what happens because there's no free neutrons hanging around in the sun. So yeah, it'd help. But so here's what happens: if you take 2 protons and try to stick them together, they don't stick. That system's called a diproton.
Whoa!
Will fall apart.
Can I take one step back?
Go for it.
Now, protons are positively charged. And how do you get them close enough together,
Oh.
right, such that they can stick? I mean, if stick, you mean the strong force, right?
Yes.
Now, that's a short-range force.
Yeah.
So you need to get protons very close together for that to happen. So how do you do that? Because I imagine protons positively charged, it's like boing and moving away.
Yeah. So they've got to be hot. Is the short story.
Hot. What does hot have to do with it?
So heat is simply a measure of how fast things are moving at the subatomic scale. So if you do your physics properly, you know how hot this bit of air here is. You know how fast the molecules of air, of oxygen and nitrogen are moving.
Yeah.
And so, given the sort of electrostatic repulsion that we'll get between protons, there's a certain speed you need for them to get close enough for the strong force to latch on before they get pushed away. So there's just a certain temperature you need for that to happen at all.
So that's why the center of the sun is already hot before the nuclear reactions start. Is because we need those protons move in fast enough that they can get close enough. So it's the squeezing due to gravity that heats up the gas, that then gets them close enough that the strong force matters, and then we get nuclear reaction. Okay, so there's already an interesting chain here. But as you said, 2 protons, when they meet, even if they get close enough for the strong force to connect them, that's not a stable system.
Yeah, the strong force won't hold them.
That's weird.
It is quite weird. And we'll come back to an especially weird bit of it in a second.
Okay.
But so here's what's got to happen. There is a short amount of time when they're coupled before they will break apart.
Okay.
So they will come close. Strong force will try and hold them, but they'll fall apart. What we need, in order for the sun to burn, is something else to happen during this time. Because if that's all that ever happened, protons would just sort of effectively bounce off each other after a very short amount of time. What happens is there's something called the nuclear weak force. It's a force that can turn a proton into a neutron and a neutron into a proton under the right conditions. Ordinarily, just leave a free neutron hanging around, the weak force will turn it into a proton. But under the right conditions, under certain rare conditions, a proton will turn into a neutron. And
Okay.
so what we need is at just the right time. Here's two protons. They come together. They stick for a little bit, and then the weak force arrives just the right time on the scene to turn one of them into a neutron, proton and neutron. And now that system is called a deuteron, and that will stick. Those are stable. Okay, so if the weak force turns up at just the right time, proton meets proton, one of them turns into a neutron, and suddenly we've got a stable thing. And because that's a stable thing, there's a binding energy, and that binding energy is released in the form of energy, which sort of is part of what powers the star.
Okay, so here's the interesting question that's bugged me. Why do a proton and neutron happily stick together to form a deuteron, but a proton and proton don't? Is it something to do with the fact that proton and proton are both positively charged?
Well, that might be the first guess. That makes some sense, right? Okay. But the problem is if you take two neutrons and try to stick them together, okay, you might think, oh, they're not repelling each other either.
Because they're neutral?
Because they're neutral. And so they should stick if that argument is right. But actually the dineutron, two neutrons stuck together, isn't stable. It's as unstable as the diproton. So that's not it.
So what is it?
So what is it? Well, it's a weird quantum mechanical thing.
Isn't everything a weird quantum mechanical thing?
Yeah, all quantum mechanical things are weird quantum mechanical things. This is an especially weird one. There's a rule in quantum mechanics called the Pauli exclusion principle. And the way it's familiar to most people is in atoms. So if you have a nucleus of an atom, the electrons go around the outside, in much the same way that these flies are going around us.
Yes. We seem to have been joined by all of the flies in Surrey.
Yeah, they're all here. And there's certain orbits that they can have, as a finite set of orbits, a discrete set of orbits, you might say, according to quantum mechanics. And so the question is, where do the electrons go? And if it were just up to energy, right, they'd all go into the lowest orbit and just hang around there. So why don't they? That's not what we see in atoms. And the answer is that there's a rule in quantum mechanics which says where you've got a type of particle known as a fermion, which has what's called a half-integer spin, but we can get back to that. You can't put two of them in the same quantum state. Not allowed. So here's the inner orbit of an atom. Right? I can put one electron in there, and actually I can make it spin one way, the same way as the nucleus. I can put another one in there, have it spin the other way, but that's it. If I tried to add a third one, it would be in the same quantum state, same energy, same spin as one of these two, and that's not allowed. And so that energy level's full. And so the next electron's got to go out further into a different state. And that's why you fill up the energy level sort of further out. This is why chemistry works, so it's quite important.
Well, for chemists.
Also for life, but mostly for chemists. So here's what how it works for the diproton and the deuteron. If you try and put two protons in the same nucleus, in the same nucleus, right? A proton and a proton. Those are the same type of particle, and so they can't have exactly the same properties. You've got to put one spin up and one spin down. And it's a funny property of the strong force that actually requires more energy to bind them together if they have opposite spins. Right? That's just something about the strong force which is kind of weird. What that means is, if you try to put together a proton and a neutron, because those are different particles, you can put them in the same system and both with the same spin, and so the strong force will bind them together a bit tighter.
Okay.
So it's this weird sort of quantum mechanical thing. It doesn't like putting the same particles in the same state, and two protons are the same particle, and so when we try and put them in the same state, they need a little bit more energy to bind them, and that a little bit more force to bind them maybe, and the strong force doesn't quite have that much.
Okay, it's an interesting quirk about our universe then, that we can have this proton-neutron, but not proton-proton, neutron-neutron, and that seems like the first step to building up all of the heavier elements. And we've already looked at this, and what happens if you did have a universe where you can put proton-proton together, or if you had a universe where you couldn't stick a proton and neutron together, and you end up with universes, some similar to our own, some very dissimilar to our own, etc. So it's a bit of a messy situation.
the funny thing is, the strength of the strong force is a number that we can dial.
Yeah.
And it doesn't take much one way or the other before actually it's still strong enough to hold together the diproton, so those are stable. Or the other way, it's not strong enough to hold together the deuteron, so it's totally unstable.
Yeah.
So you could have a universe in which all three ways of putting together proton and neutron, proton, 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 neutron, 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 they're all stable. Or you can have one where they're all unstable, and that's sort of most of the strengths of the strong force, except for this funny little range in the middle where we are, where proton, proton, neutron, neutron are unstable, proton, neutron is stable. The
Close
deuteron
to
is
the edge,
stable.
right? Close
Yeah,
to the
it's
edge.
weird.
No, but I just remembered an interesting fact. So the fact that we are relying on this situation where two protons come together, there's a very small chance that one of those protons gets flipped into a neutron. That's the first step of the cooking of elements in the sun. Because the weak force is weak, that means that change to a neutron is a rare occurrence, and that actually makes the sun highly inefficient.
Yes.
Right? So the energy production in the sun is less efficient than a compost heap in the amount of energy produced per kilogram.
Right, yeah.
And people get amazed by this, but you forget that there's a lot of mass in the sun. But this helps, right? It really helps because it means that the sun is very long-lived. It takes 10 billion years for the sun to burn through its fuel. Right? A smaller star, it might take 1 trillion years. So the sun is long-lived because, at some level, the nuclear force is very inefficient. If the weak force was more efficient at flipping protons into neutrons, then the fires would probably burn a little bit faster.
Yeah, but one of the interesting things we found was it's not that much faster.
It's not that much faster.
So, for example, one of the ways in it's really inefficient is proton meets proton in the sun. How many times has that got to happen before they make that deuteron? And the answer is an enormous number, something like there's one successful reaction for every 10 to the 22 times that they meet, which is kind of amazing. If instead 10 to the 22, 10 to the, it's some enormous 10 to the 20-ish anyway. It's some enormous number. If instead the diproton were bound, if you could stick two protons together, basically that number would change to be it'll just happen every time. And what was argued in the 70s was actually a very early supposed case of fine tuning, is that this would make stars explosive. Stars collapse, they heat up. Suddenly, every time a proton hits a proton, it releases energy. And because the reaction is so much faster, 10 to the 18, 10 to the 20 times faster, it was argued that stars would burn out that much faster. Which would basically mean, if the diproton were bound in the sun right now, it would burn through all of its fuel in about 1 second.
Yes, which would be bad.
Very bad indeed, as opposed to sort of 10 billion years that we got. But it's not quite that bad because if you just sort of cool the sun off a bit and make it expand a bit more, like make it bigger and less dense, the reactions will drop. And those very fast reactions just make a star which... Actually, the lifetime's not too much different. The main thing is that you could actually fire up a smaller ball of gas.
Yeah. So yes, this is one of the issues: is that the sun is not a fixed thing. It's a system in equilibrium.
Yeah.
Gravity squeezing, heat in the core, nuclear reactions. So if you had more efficient nuclear reactions, you could do less squeezing, have a bigger, fluffier star, etc. So it is a bit more complicated, but it still is one of those interesting things.
Yeah.
But we should get back to the topic.
Right.
We've formed a deuteron.
Okay.
What else happens in the sun?
Well, the nice thing from here is that the rest of these reactions don't rely on a sort of that weak force miracle happening at just the right time. So you've now got protons, you've got deuterons. We can throw those two together to make what's called helium-3, two protons and a neutron. Two helium-3 particles can come together to make a helium-4 particle. 2 protons, 2 neutrons, and a couple of other things. I think 2 protons come out, something like that. And once you've got helium-4, that's a very highly, strongly bound thing.
Yeah.
So when you make that, lots of energy gets released. So actually, that's the reaction in this chain which releases most of the energy we see in the sun.
Okay.
So it's of a total amount of energy, that's probably about 90%, 95% of it.
Okay.
So that's the chain. The rest of that happens pretty quickly. So you wait around an awfully long time to make that deuteron, but then you burn and make a helium-4 particle almost instantaneously.
Okay. Now, look, the day's just beginning here, and we've got to get to work, so we should probably wrap this up.
Yep.
There's a lot more to talk about with the generation of energy in stars, and we'll talk about what goes on in bigger stars and how we forge the heavier elements later on.
Yep.
But I think for today, let's go and enjoy some of the Surrey sunshine.
Yes, it's looking lovely.
Yes.
So there's a lot of flies. Is it me?
It is you. Okay.
Take the boy out of Australia.